All right, part 2 of the 2.1.6 truss force calculations, we're going to do our internal forces. So just as a quick reminder, we have the assumption that all members are in tension until we find that one of our internal forces is negative. In that case, that member is then switched to being in compression. So first step of, again, any truss problem is drawing your free body diagram. But in this case, we're using that method of joints. That method of joints says that we pick a certain joint, or we go through each A, B, C, D, each joint, and look at each case and look at what members are being acted upon by what forces, and therefore determining what amount of internal force is on each of the members. So in this case, I already started my table, so the general free body diagram, or just diagram. This is not the free body diagram. This is given to you in the problem statement. Typically, what you would want to draw in is this box here. I don't have it boxed in, but all the unknown values that you will eventually find, you'll want a nice clean box. So part 1 looks like this. We had a box in the upper right corner. So we're going to go on to solving this one, internal forces. We're going to look at joint A is where we're going to start. So if we look at joint A, our free body diagram looks something like this. We've got the point itself, the joint itself, then we have member AB coming up to the right, AD directly to the right. I'm actually going to redraw that just real quickly, just because I need more room to write some values in. This is point A. We had the reaction force of A in the x direction. We had reaction force at A in the y direction. And that was it. So we could plug those in. If you look at our table, reaction force A in the x direction was 0, A in the y direction was 350 pounds. So I'm going to note that. Pound force there. This was 350 pound force straight up. Wow. Okay, so our first step is going to be looking at this saying, do we want to solve this in terms of summing the forces in the x direction or summing the forces in the y direction? Because we know that both of them sum to 0. I could probably also put in here the angle. So in doing that, we have to break component AB from its angle into its components x and y. In doing that, we've got this. This is AB itself. This is our ABX. And our ABY. And our angle. So when we go to find, in this case, since we have reaction force A in the y direction is 350 pounds, let's do the summation of the forces in the y direction first. We know that they have to equal 0. The only two forces that we have right now in the y direction are reaction force AY, subscript, and that's a positive because the arrow is pointing up, and the y direction of component AB, simply stated AB in the y direction, which is also pointing up, so they're both positive. We can substitute in and say that 0 is equal to 350 plus AB in the y direction. Well, how do we solve AB in the y direction? Well, what we're going to do is we're going to solve for AB in the y direction. Let's try this back. Sine of 53.13 degrees is equal to AB in the y direction over the full magnitude AB. So AB in the y direction is equal to AB times sine of 53.13 degrees. So we have our ABY in terms of our magnitude AB, which is what we need in the end, the full internal force of AB. So that's why we're substituting ABY in and using magnitude AB. So what I'm saying is we have 0 is equal to 350 pounds force plus ABY, which is actually the internal force AB times sine of 53.13 degrees. So in simplifying, internal force AB is equal to negative 350, because we're going to move 350 pounds to the left. We're going to divide the whole thing by sine of 53.13 degrees. And we find that AB itself equals negative 438 pound force. So what we found is this arrow that is showing AB in tension is actually wrong. So when I go to fill out my table down here, my AB should actually, you always write it, what happened? Here we go. You always write internal forces as positives, but then you note in parentheses a C for compression or a T for tension. But again, because we found a member in negative pound force, what that's telling us is that our initial assumption that everything is in tension is telling us that we were wrong. The negative says we were actually in compression. So again, we write our answer as positive 438, and then we note it as in compression. So just real quick, what we can do then with that information is we can now take and sum our forces in the x direction, because we know those equal 0. And what we have is we have the reaction force AX, which is to the right, which is positive, plus we have member AD, which is positive also, because that's pointing to the right. And that's the full internal force of member AD. There's no trigonometry required, because it's directly along the x-axis. Plus then, no, I'm sorry, we need to update this. We would say that it's to the right and up when we initially assume tension, but because we have to update this free body diagram, this one's actually in compression. So our AB, our member AB, is going to be a negative. So I'm going to say minus the x component of AB. Okay, so we would have said plus AB in the x component if it was in tension. Because it's not in tension, it's actually in compression. We switch the arrow, which puts our x to the left. So what we can do is say that yes, this is all equal to 0. What we know is that reaction force AX was an external force of 0. So we can update that. 0 plus AD. Well, AD, we have no clue what it is. But AB in the x direction. Well, let's see. AB in the x direction we can solve that as AB cosine of 53.13 degrees. So let's look at that. That's AB cosine 53 degrees. Well, we don't know AD, but we do know AB. We just found the magnitude AB. So let's keep updating this. Plus AD minus AB, which was 438, times cosine of 53.13. Oops. New ones there. There we go. And again, that equals 0. So we're going to add 438 cosine 53.13 to the left side, and we get positive 438 cosine of 53.13 equals AD. So you run your calculator through, you find 438 cosine of 53.13 is 262.5 pound-force. AD is already positive when we solved for it. So our assumption that it was in tension is true. So we go down to our AD. Let's see. I messed all those up. I forgot I hadn't updated this. So we have members AB, AD, BC, CD, and BD. There we go. Some of you may have been watching this entire video thinking, what are those members referring to? I had relabeled my letters before I started the video, but I never updated my table. So now we have AD 262.5. That was already positive, so that 262.5 stays in tension. Alright, that is joint A. And we've solved for AB and AD. I would recommend our next point that we work with is joint C. And by doing joint C, we would find moment, or internal force at BC and DC. And all that you would have left is moment. I keep saying moment. The joint D, we could find the internal forces there, while the three internal forces at point D, joint D, is AD, which we already solved, and CD, which we would solve at joint C. So our third joint that we would calculate all of our internal forces at, we're just left with BD. So in this case, we don't go around to all four joints and do our internal force calculations. We did moment point A and found two members. We go to point C, we find two members. We would just go to D to find our fifth member. I'm going to stop this video here. I'll walk through the last three internal forces for BC, CD, and BD in part 3.